Hello, everyone. So starting from today, for the next couple of hours, we are going to explore network-based project management and scheduling method. Just to let you know, many important real-world optimization problems can be analyzed effectively by means of a network representation. So our discussion will be mainly focused on the critical path method, or CPM. Okay, so let me share my screen first. Oh. Okay, so is it right? Okay. Okay, so okay, so let's just talk about briefly some terminologies. So the project, what is project? Project is defined as a collection of interrelated activities or tasks directed towards the accomplishment of a goal or an objective. And of course, each task consumes time and resources, right? The project management is a system of procedures which provides for planning, scheduling, and control of a project. Okay, so there are two types of network models for a project scheduling or project management. So one is activity on arc or activity on arrow model, in which tasks or the activities are represented by arcs or arrows in the network model. And the other one is the activity on node or AON model, where the tasks or activities are represented by nodes or vertices in the network model. Okay. Oh, okay. So before we talk about the activity on ARC network model, which has been widely used for CPM, critical path method, that we are going to talk about in a bit. Let me give you a background information about the Gantt chart and CPM PERT just briefly, okay? So the Gantt chart, probably the simplest and also very widely used scheduling techniques today. And the American engineer Henry Gantt developed a bar chart, which is called the Gantt chart later in 1917 as a visual production scheduling tools. Okay. And so as you can see in this diagram, the Gantt chart is a rectangular diagram, consisting of a horizontal axis for time unit and a vertical axis for either task or the activities, okay? And in the diagram, tasks are listed usually on the left-hand side, and the time scale along the either bottom or the top. So in this case, it shows on the bottom, right? And the position and the length of the bar reflects the start date or start time and duration and end date or end time of the activities. Okay, and Just to let you know, the Gantt chart indicates the tasks and the time in a graphical format like this, and which allows the allocation of the time, allocation of the actually, what is that, the task or the activities in time horizon. But the problem is, it's not easy to show the interdependencies between each tasks or the activities. And it also didn't show which tasks are the critical to finish the project on time. So this is where the CPM, the critical path method, comes in. Okay, so the critical path method, or CPM, and the program evaluation or project evaluation and review techniques, the PERT, were both developed simultaneously in the late 1950s. Okay, and although they are very similar to each other, they were developed for fundamentally different business spheres. And the origin of the CPM may be traced back to 1956, DuPont in the United States. And they were one of the, the very first owners of the computers installed in a commercial business. And they were looking for useful activities to do with their own computers. So they want to determine the best trade-off between the time and the cost. So they developed a model for the time cost problems. And they demonstrated that the focusing efforts on the critically important activities could reduce time without significantly increasing cost, instead of recovering lost times with a bulk of labor. So, of course, the challenging task was to determine the critical activities. By the way, they used what it called the activity on arc or activity on arrow, AOA network model, to explain the calculation of the method. And of course, we are going to talk about it in a minute. Since then, the CPM, the critical path method, was become more focused on the scheduling side rather than the cost. And it's been widely used in various consulting firms, and also aimed for the construction and maintenance in the industries, where the processes are very well known ahead of time, and the estimations of the task durations could be done with some accuracies. So, if the duration of each activity is known with certainty, then the project completion time can be found using the CPM critical path method. Okay, and the critical path method also can be used to determine how long each activity in project can be delayed without delaying the completion of the project. Okay. Next is about the PERT. So in contrast to CPM, the PERT was mainly focused on the military research, okay, where the time pressures were very high, and the cost would be the secondary issues in that case. So in a military research environment, the duration of each activities were very difficult to estimate, right? So the PERT emphasizes to estimate the probability, that the project will be completed by a certain given deadlines. Okay. Okay, so the CPM and PERT have been successfully used in many applications, real-world applications. That includes the scheduling, the construction project, like office buildings, highways, and swimming pools, kind of thing. And also installing a new computer systems and building a ships, and airplanes, and so on. Okay. This diagram shows an exploded view of a certain camera, and this is one of the GM cars diagram, parts diagram. So where the CPM and PERT, the project scheduling method was successfully implemented. Okay. Okay, so okay, now let's take a very simple example. So suppose a manufacturing company is about to introduce a new product. Okay, so let's call this a product number 3. Okay, so this is product number 3. Okay. So this is the product number 3. Okay. And we've known that 1 unit of product number 3 is produced by assembling 1 unit of product number 1 and number 2. So let's say this is product number 1, and this is going to be product number 2. Okay. And the list of activities or the tasks associated with the introduction of the product number 3, and together with the estimated duration and the immediate predecessors are given in this table. Okay. So according to this table, so if you look at the precedence relationships on this table, we may say that before production begins on either the products number 1 and number 2, the raw materials must be purchased, right? And the workers must be trained. That is, both activities, C and D, have 2 predecessors. They are A and B, right? Like this. Likewise, before assembling products number 1 and 2 into product number 3, the finished product number 2 must be tested, must be inspected, right? And you are required to do the tasks for the completion of this whole project, okay? So by using Gantt chart, we can show the activities or tasks displayed against the time like this, right? So each task or activity in Gantt chart is represented by a bar, right? Which specifies the beginning and ending of each activities or task. So the duration of each activities, right? And of course, the Gantt chart allow you to see when each task begins and ends, and how long each task is scheduled to last, right? And where tasks or the activities overlap with other tasks, and by how much, right? And of course, the start and end date or end time of the whole project can be seen as well. But what's the problem? The Gantt chart does not show the dependencies of the task to each other, even though it is possible to do that, but it's not easy compared to the CPM. Okay, and also the Gantt chart doesn't show which tasks are the critical to finishing the project on time. Okay. Okay, and if we draw a project diagram, network diagram for this project, then it will be just like this. Okay. So the CPM is based on the network diagram, the AOA model and AON model, right? And the AOA model, if you recall, the activities are represented by directed arcs or the arrows. And in the AOA model, the nodes are used to represent the completion of a set of activities. In other words, the AON network model, the activities are represented by nodes. And the directed arcs are used to represent the completion of a set of activities. Okay. And just to let you know, our discussion in this class will be mainly focused on the activity on arc or AOA model, simply because its network structure is more suitable for the analytical techniques and the optimization formulations later, not only for the CPM, but also for other network optimization models. Okay. So we're going to talk about the AOA model more in detail. Okay, and if you'd like to know the shortest time required for the whole project, in our case, for the production of the product number 3, then if the duration of each activity is known with certainty, then the critical path method, CPM, can be used to determine the length of the time required to complete the project. And if the duration of the activity is not known with certainty, then the program evaluation or project evaluation and review technique can be used to estimate the probability that the project will be completed by a given deadline. Okay. Okay. So given a list of activities and predecessors, the activity on arc model or AOA representation of a project can be constructed by using these rules. Okay. And just to let you know, to avoid violating the last 2 rules, it is sometimes necessary to utilize a dummy activity that takes 0 time. Okay, and I will explain you with some examples later. Okay, so okay, the network, the project network indicates the order in which the activities or the tasks may be performed. So to understand how an AOA network activity on ARC network represents the precedence relationship, let's consider a simple AOA network model like this. So this definitely represents the activity A is a predecessor of activity B, right? Also, we know that the activity B is a successor of activity A. So in this case, each node in an AOA network represents the completion of one or more activities, right? So the node number 2 in our case represents the completion of activity A and the beginning of activity B. So the activity B, of course, cannot begin until the activity A has been completed. Is that right? Okay. Now suppose activity A and B must be completed before activity C can begin. Then how do you express this relationship by using a AOA network diagram? So in this case, if I have node 1 and 2 down here, and I have activity A and activity B, right? And then I'm going to have event number 3. And I have activity C, something like that, right? So here, in this case, node number 3 represents the event that both activities A and B are completed, right? Oh, sorry. Okay. So let me delete this so you can clearly see that. Okay. 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 Now if activity A must be completed before activities B and C can begin, then how do you express this relationship using AOA network diagram? How about this? So it shows that activity A is a predecessor of both activities B and C. Is that correct? Okay, then how about this case? Let's suppose activity K must be completed before activities A and B can begin. So we have this AOA network diagram. Now we have to consider, we have to add one more precedence relationship, which is activities A and B are both predecessors of activities C, and they can begin at the same time. Then how do you complete the network diagram here? Like this. Okay. So what if I have event 3 here and then activity C? Then make a connection like this. Does that work? Earlier, I mentioned that given a list of activities and predecessors, the AOA representation of a project can be constructed by using these 3 different rules, right? Of course, in the absence of the last rule for constructing the AOA network diagram, that there is 2 nodes in the network diagram can be connected by at most 1 arc. Then this network diagram is okay, right? However, because nodes 1 and nodes 2 and 3 in this case are connected by more than 1 arc, right? Which violates the rule number 3, obviously, right? So what you need is to introduce or utilize the dummy activity, okay, here. And the dummy activity has to work content. I'm sorry, the dummy activity usually takes 0 times, and it doesn't have any the work contents in it. And it's usually drawn with a dashed line. So by using the dummy activity, our case can be handled like this. So this is K2. And if I say, okay, this is going to be A, and this is going to be B, then I'm going to introduce dummy activity with a dashed line here. And then we have C. This is going to be 3 and 4, for example. Okay. So in that case, activity A is completed before activities A and B can begin, right? And activities A and B are both predecessors of activity C, right? And begin at the same time, like this, okay? So this network diagram does fulfill these 2 given conditions without violating any rules down here, okay? So this is wrong and this is correct, okay? Okay, then what about this case? How do you express, how would you construct the AOA network diagram to express that activity K must be completed before activities A and B, A, B, and C can begin. And activity D has also 3 predecessors, which are activities A, B, and C. So some of you might do this. So if I say this is activity A, this is activity D, and this is going to be activity B, and activity C. Then with the same reason here, two nodes can be connected by at most one arc. So this is going to be wrong diagram, right? So again, utilizing the dummy activities, there is no zero time, there is no time in that. So we have 1, 2, 3, and this is activity A. And then you have activity B. And we have dummy activity here that has zero time. And then what about, we have activity C here, and then another dummy activity down here. So if I say this is 3, 4, then this is going to be 5, for example. And then we have activity D, okay? So, and also keep in mind that only one activity is allowed between two vertices, right? So here, only one activity is allowed. Also, between these two vertices, only one activity is allowed, right? Likewise, between these two events, only one activity is allowed, right? So in this case, we introduced dummy activities, right? With zero duration. So if I say this is dummy 2 and dummy 1 here, then both of them has zero duration. Okay, then what about this case? So activities A and B are predecessors of activity C, but only B is a predecessor of D. So how about this? 1, 2, we have, and then we have activity A and B, like that. And so if I have C like that, then actually in this case, both activities A and B are the predecessors of C, right? What if you have D down here? In this case, again, both activities A and B is the predecessor of D, right? However, it does say only B is a predecessor of D. So this diagram doesn't satisfy the second part of the condition, right? So this is wrong. So in this case, again, we introduce dummy activity with zero duration to satisfy both conditions, okay? So in this case, if I have A and B like that, and then what if I have dummy activity like this, and I have activity C? So in a way, both activities A and B are the predecessors of C. And if I have activity D down here, in this case, the only B is a predecessor of activity D, right? That makes sense? So I can level 3, 4, maybe I have 5 and 6, something like this, okay? So that's going to be the correct network diagram. Does that make sense? Okay, now let's move on to the some terminologies that can be used for the CPM, critical path method, later. Okay, so there are two key building blocks in the CPM. They are the concepts of the ET, earliest event time, or earliest time, okay, for certain node I, and that is represented by ET sub I, okay, and that is the earliest time at which the event corresponding to node number I can occur. And the LT stands for the late event time, or the latest time. And that is the latest time at which the event corresponding to node I can occur without delaying the completion of the project. So in other words, the late event time, or latest time, is the latest time at which event I can occur with the project is to be completed in minimum time, okay? And also we assume that the beginning of project be the event number 0, and the end of the project be the event number n. And also for each activity, we define the earliest start time and earliest finish time, earliest latest finish time, and latest start time, like this. Okay. Okay, so to define the early event time, earliest time for each node in the network, in the project network, we begin by noting that the earliest time for event number 0 would be equal to 0, because node number 0 represents the start of the project, okay? And then we were gonna compute the earliest time for event number 1, 2, 3, and so on. And then we're gonna stop when the event earliest time for the final node has been calculated. Excuse me. So to illustrate how the earliest time can be calculated, let's consider a segment of the AOA network project diagram like this. So we assume that we already have known that the earliest times for events number 3, 4, and 5 are given as 6, 8, and 10, okay? And we'd like to determine the earliest time for the event number 6. Then how do you get it? So to determine the earliest time, we use this computation. So the earliest time that the node number 6 can occur would be the 14, because that's the maximum value among these three. Okay, and we observe that the earliest time that node number 6 can occur is when all of these three activities corresponding to arcs 3, 6, and 4, 6 and 5, 6 have been completed, right? Because the node number 6 represents the event that all of the activities A, B, and C is completed, right? So that's why we have to take the maximum value among these three. Okay, that's going to be 14 in this case. So it's clear to say that the earliest time for the final node is the length of the longest path in the project network from the start node to the finish node. Okay. Okay, now let's talk about the latest time or the late event time, and that is represented by LT. Okay, so to find the latest time or the late event time for each node, we begin with the finish node and then work backward, okay? So in descending numerical order until we determine the latest time for the start node, which is the node number 0, okay? So for example, if we determine the project can be completed in 38 days, then the latest time for the finish node automatically becomes 38, okay? And then we do the backward computation until we reach to the start node, which is node number 0. Okay, so likewise, we did for the earliest time to illustrate how the latest time is computed for nodes other than the finish node. Suppose we are working with this network diagram. So for each, we have already determined the latest time for nodes number 5, 6, and 7, okay? Those are given as 24, 26, and 28 days, okay? Then how can we compute the latest time for node number 4 here? So in this case, so in this case, let's suppose the latest finish time for events number 5 would be using this number. So it's going to be, let's say, 11:24 a.m. And the latest finish time for event number 6 would be 11:26 a.m. Okay. And the latest time for event number 7 would be 11:27 in the morning. Okay. And let's also assume that 3, 4, and 5 minutes are required to conduct the activities number A, number B, and number C, respectively. Okay. And if the event corresponding to node number 4 occurs after 11:21, which is from 11:24 a.m. minus 3 minutes. Okay, so in this case, what I did is LT five minus 3, right? Here LT5 is 11:24 a.m., right? Minus 3 minutes, right? Then what happened? In that case, wait a minute. Okay, I think that is correct. Okay, so sorry. So if the event corresponding to node number 4 occurs after 11:21, which is from this computation, right? 11:21 a.m. That is from 11:24, right? Minus 3 minutes, right? 11:24 minus 3 minutes. Then the node number 5 will occur after 11:24. That is the latest time for event number 5, right? And in this case, the completion of the project will be delayed. Is that correct? Similarly, if the event, even if the node number 4 occurs, event number 4 occurs after 11:22. So this is from 11:26 minus 4 minutes. So 11:26 is from here, and 4 minutes is from here, right? So this is same as LT, the latest time for event number 6 minus 4 minutes, right? Which is down here. Or if the node number 4 occurs after this, which is from 11:27 minus 5 minutes, which is this, right? Actually, it's 11:28. Sorry, I copied the wrong number, so it's going to be 11:28, right? So 28 minus 5 becomes 23, right? Then the completion of the project will be also delayed. So the latest time that node number 4 can occur has to be the minimum number among these 3 different values, okay, which is 21. So here, latest time for event number 4 should be 21, okay? Sorry, I made you confused earlier, but again, if I repeat this, then if the event corresponding to node number 4 occurs after 11:21 or 11:22 or 11:23, then the completion of the project will be delayed. Is that right? So the latest time that node number 4 can occur has to be the minimum value among these 3 different values. It's going to be 21. So keep in mind that when you compute the latest time, you always go with the minimum value, okay? However, when you compute the earliest time, you always go with the maximum value, okay? And what is that? Okay, so the next concept is about the total float. So for each activity in the AOA network diagram, we define the total float, so which is the represented by TF. That's going to be the latest start time minus the earliest start time. Okay. So for an arbitrary arc representing the activity ij, the total float represented by TF ij is the maximum possible time by which the starting time of the activity ij could be delayed beyond its earliest possible starting time, okay, without delaying the project's completion time. Of course, assuming no other activities are delayed, okay? So equivalently, the total float of an activity is the amount by which the duration of the activity can be increased without delaying the completion of the project, okay? So if an activity has a total float of 0 value, then any delay in the start of the activity or the duration of the activity will delay the completion of the project. So in fact, the increasing the duration of the activity by, let's say, alpha days will increase the length of the total project by alpha days, okay? So such an activity is very critical to the completion of the project on time, right? So any activity with a total float of 0 value is called a critical activity, okay? The path from the start node to the finish node that consists entirely of critical activities is called a critical path, okay? And because any delay in the duration of a critical activity will also delay the completion of the project, it is advisable to monitor very closely the completion of the critical activities, okay? Okay, so now let's take a simple example. So this example will help you clarify the notion of the critical path scheduling that we've just discussed, okay? So let's suppose a list of activities required for a certain project and the immediate precedence relationship and the estimation of the activity durations are provided in the table. Just to let you know that to apply the critical path method, we need a list of activities that make up the project together with the precedence relationship and the activity durations, right? Okay. Let me close this on my camera. Okay, so like I said, for each activity, there is a set of activities which is called the predecessors of the activity that must be completed before the activity begins. Okay, the project network is used to represent the precedence relationships between the activities or the tasks. Okay. So just keep you remind that all of these three items, the list of activities and the precedence relationship and the estimation of the activity durations, all these three items are necessary information to construct any AOA network diagram. Okay. Okay, so this is the AOA network diagram for this given information. So I want you to record that in the AOA network, activities are represented by a directed arc, right? The nodes are used to represent the completion of a set of activities, okay? So for this reason, the nodes in the project networks are referred to as events, okay? So in this case, we have 4 different events. Events number 0, 1, 2, and 3, okay? And also the project is considered to be completed when all of the activities have been completed, okay? So usually node number 0 represents the start of the project. And an arc should lead from this node number 0 to each activity that has no predecessors. So in our case, because both activities A and C has no predecessors, right? That's why we have 2 arc directed from node number 0, okay? And also node called the finish node in our case, node number 3 represents the completion of the project, has to be included in the network diagram, okay? What else? I think that's it, right? Okay, now I'm going to use these notations for each activity, okay? So for each activity, I'm going to specify the 60 different values, okay? Earliest start time, latest start time, earliest finish time, latest finish time. And I'm gonna put the activity duration right here, and then activity name down here, okay? Okay, so here, A, B, C, D, and E's are the activity name. And the 3, 7, 2, 5, 1 are the corresponding activity duration, right? And we are going to fill in earliest start, earliest finish, latest start, and latest finish time for each activity, one by one, okay? Okay, so the first starting as time t equals 0. The earliest time for the start node becomes 0, right? So we have 0 down here. And the earliest start time for both activities, A and C, becomes 0 because of that, right? So this value transferred here and here automatically, right? And then earliest finish time right here for activity A is going to be 3, which came from is earliest start time plus its duration. Okay, so 0 plus 3 becomes 3. Okay. Likewise, the earliest finish time for activity C should be 2. That's from 0 plus 2, right? Becomes 2. Yeah. And the event, the earliest time for event number 1 becomes 3, which is from the latest finish time of activity A down here. So this value automatically becomes the earliest time for event number 1. Okay. Because in this case, the event number 0 represents the completion of the activity A. So that's why the earliest time for event number 1 is going to be 3, which is from here. Okay. And the earliest start time for both activities, B and E, becomes 3, which is from here directly, right? And the earliest finish time for activities B is going to be 10, which is from 3 plus 7, right? Likewise, earliest finish time for activity E going to be 4. That's going to be 3 plus 1, right? Becomes 4. Now we need to determine the earliest time for event number 2. We need to take the maximum value between 4 and 2. Because here, node number 2, the event number 2 represents the completion time of both activities E and C, right? So that's why the maximum value between these two values becomes the earliest time for event number 2. So in this case, 4 will be done, right? Does that make sense? Okay, now let's move on. And the earliest start time for activity D becomes 4, right? And the earliest finish time for activity D becomes 9. There is 4 plus 5 becomes 9 here. Again, we need to determine the earliest time for event number 3. And we take the maximum value between these two values, right? 10 and 9. Because again, the event number 3 represents the completion of both activities B and D. So we have to take the maximum value between these two. So this way, we can compute the earliest time, okay, for this AOA network diagram. Okay, now I'm going to show you how to compute the latest time for each event. Okay. Okay, so to compute the latest time, we begin with the finish node and working backward until we reach the latest time for the start node. Okay. since we know the project can be completed in 10 days, the latest time for event number 3 becomes 10 automatically, okay? And the latest finish time for activities B and D becomes 10, right? And the latest start time for activity B is going to be 3. That is from the latest finish time minus its duration. So 10 minus 7 becomes 3. Likewise, the latest start time for activity D becomes 5. That is from 10 minus 5 becomes 5. Okay. And the latest time for event number 2 becomes 5 from the latest start time of activity D. Okay. And the latest finish time for activity C becomes 5. And the latest start time for activity C is going to be 3, which is from 5 minus 2 here, right? And the latest finish time for activity E becomes 5. That is from here, right, directly. And the latest start time for activity E is going to be 4, which is 5 minus 1, right? Now we need to determine the latest time for event number 1. And we need to take the minimum value between 3 and 4, right? Because activity A must be completed before activities B and E can begin. So the latest time for event number 1 becomes 3, which is from the latest start time of activity B. So we took the minimum value between these two. Okay, so that's going to be 3. And the latest time for activity A becomes 3 from here, right? And the latest start time for activity A becomes 0, which is 3 minus 3 becomes 0. Again, now we need to determine the latest time for event number 0. Again, we need to take the minimum value between 3 and 0, right? Because node number 0, event number 0 represents the activities, both activities A and C can begin, right? So the latest time for event number 0 becomes 0. That is the smaller value, right? Between these two, which is 0. Okay, now we've obtained the latest time for each event. And earlier, we've learned that any activity with a total float of 0 is a critical activity, right? The path from start node to the finish node, that consists entirely of critical activity is called a critical path. So how do you compute the total float? So the total float can be easily computed. That's going to be simply the difference between these two numbers. Earliest start time and latest start time, okay? Or the difference between these two numbers. Earliest finish time and latest finish time, okay? So in this case, the difference is 0, right? Also here, the difference is 0, which means the corresponding activity A has to be one of the critical activity, okay? But here for activity E, there is a positive gap between these two numbers, right? Which means activity E cannot be the critical activity. This is not the critical activity. For the same reason, activity C and D cannot be the critical activity. But for activity B, there is no difference between these two numbers, right? There is no differences, right? 0 values differences, which means in our case, both activities A and B are the critical activities, okay? And in this case, the path 0, 1, and 3 going to be the critical path for this example problem. And just to let you know, it's possible for a network to have more than one critical path, okay? And also the critical path in any project network is the longest path from the start node to the finish node. Because, when you compute the earliest time, you remember we always take the maximum value, right? That's why the critical path would be the longest path from the start to finish node. And any delay in the duration of a critical activity will delay the completion of the project. So again, it's very, very important to monitor very carefully the completion of the critical activities, okay? Okay, then I will stop here for today. And next time we will continue to talk about the CPM, critical path method, with some example problems. Okay. Okay, thank you. I will see you next time. Bye.